Hello everyone. Today we are diving into one of the most extraordinary and counterintuitive mysteries in all of astronomy. A celestial object, so impossibly cold that it breaks the fundamental temperature limit of empty space itself. For decades, we've understood that the universe has a baseline chill, the cosmic microwave background, the faint leftover heat from the Big Bang, which sits at a frigid 2.7 Kelvin, or about -270.45 degrees Celsius. This is the default temperature of the darkest, emptiest stretches of space, a constant that astronomers have treated as the cosmic floor for as long as we've been able to measure it. But there is a single exception, a tiny corner of our galaxy where temperatures plummet even lower, a place so cold it defies every basic assumption we have about thermal equilibrium in the cosmos. This is the Boomerang Nebula, the undisputed, coldest natural place in the entire known universe, where the thermometer drops to just 1 Kelvin, a mere 1 degree above absolute zero, the point where all molecular motion stops entirely. At -272.15 degrees Celsius, this nebula is not just cold. It is colder than the empty vacuum of space, colder than any other cloud, star or planet we have ever observed, and it stands alone as the only natural object ever found, with a temperature below the cosmic microwave background. To truly grasp how astonishing this is, we need to start with the basics of cosmic cold. Absolute zero, defined as 0 Kelvin, is the theoretical lower limit of temperature, where particles have no thermal energy left to move. Nothing in nature can reach absolute zero, but the Boomerang Nebula gets closer than anything else we know. Imagine the coldest winter night on Earth, where temperatures drop to -40 degrees Celsius. That is barely a light breeze compared to the brutal chill of this nebula. Even the darkest, most remote pockets of interstellar space, far from any star or galaxy, stay warm, by comparison, held at the 2.7 Kelvin floor, set by the Big Bang's afterglow. The fact that a natural object can drop below this threshold is not just a curiosity, it is a revolution in our understanding of how gas, energy, and stellar death interact to create extreme environments in the cosmos. The story of the Boomerang Nebula begins thousands of light-years from Earth, in the constellation Centaurus, a bright star-rich area of the southern sky. It lies roughly 5,000 light-years away from our solar system, close enough for our most powerful telescopes to study in detail, yet far enough to remind us of the vast scale of our Milky Way galaxy. The nebula was first discovered in 1980 by astronomers Keith Taylor and Mike Scarrett, who used a ground-based telescope in Australia to spot its faint curved structure. The asymmetric bent shape they observed reminded them of a boomerang, the traditional hunting tool of indigenous Australian cultures, and so the name Boomerang Nebula was born. For nearly 15 years it was just another faint planetary nebula candidate, a blurry patch of light in the sky that drew little special attention. All that changed in 1995, when astronomers Raghavendra Sahai and Lars Nyman used the 15-meter Swedish ESO submillimeter telescope in Chile to measure its temperature with unprecedented precision. The results shocked the entire astronomical community. The nebula's temperature was not just low, it was 1 Kelvin, colder than the cosmic microwave background, a finding that rewrote the textbooks on the coldest places in the universe. As technology advanced, our view of the Boomerang Nebula transformed dramatically, revealing that its original name was something of a cosmic trick. In 1998, the Hubble Space Telescope captured a high-resolution image that showed the nebula's true form, a symmetric, elegant, bow tie or butterfly shape, with two distinct lobes of gas stretching out from a central star. The curved boomerang shape, seen from the ground, was just an optical illusion caused by the limited resolution of early telescopes. Then, in 2013, the Atacama, Large Millimeter or Sub-Millimeter Array, or ALMA, peered even deeper, showing that Hubble's view was only the inner core of a much larger, nearly spherical cloud of gas, extending far into space. This layered structure is key to understanding why the nebula is so impossibly cold, as it tells the story of a star in its final violent death throes. The Boomerang Nebula is not a static cloud of gas and dust. It is a dynamic, rapidly expanding structure, created by a dying star at its center. The central star was once similar in mass to our Sun, but it has now entered the late asymptotic giant branch, or AGB phase of its life, the final stage, before it becomes a white dwarf. As stars like this run out of hydrogen fuel, in their cores they swell into red giants, their outer layers becoming weakly bound to the core by gravity. Over the past 1,500 years, this star has been shedding its outer layers at an astonishing rate, about 1,000th of the mass of our Sun, every single year, adding up to nearly 1.5 times the mass of the Sun lost in total. This material is not drifting gently into space. It is being blasted outward at speeds of more than 500,000 kilometers per hour, fast enough to travel from Earth to the Moon in under an hour. This extreme rapid ejection is the secret behind the nebula's record-breaking cold. The physics behind this cosmic deep freeze is called adiabatic cooling, a process you might have experienced in everyday life without realizing it. If you've ever held a spray can or a compressed air duster and felt the nozzle turn cold as you release the gas, you've witnessed adiabatic cooling in action. When a gas is allowed to expand rapidly into a larger volume, its molecules spread out, losing kinetic energy and dropping sharply in temperature. On Earth, this effect is mild, but in the airless, zero-pressure vacuum of space, the effect is amplified to an extreme degree. The gas, ejected from the central star of the Boomerang Nebula, expands so quickly and violently into the surrounding void that it sheds nearly all its thermal energy, cooling far beyond the temperature of the cosmic microwave background. Unlike other nebulae, which can be warmed by radiation from nearby stars or the central star itself, the Boomerang Nebula has no such external heat sources to offset its rapid cooling, allowing it to maintain its status as the universe's coldest natural location. Recent studies using ALMA have even suggested that a companion star may have plunged into the red giant, triggering the unusually fast mass loss and making the cooling effect even more intense than it would be from a single star alone. This nebula is more than just a cosmic oddity. It is a critical laboratory for studying some of the most important processes in stellar evolution. The Boomerang Nebula is a pre-planetary nebula, a short-lived transitional phase that lasts only about 1,000 years between the AGB star phase and the full planetary nebula phase. During this brief window, the ejected gas is still cool and neutral before the central star heats up enough to ionize the gas and create the bright, colorful structures we associate with planetary nebulae. Studying the Boomerang Nebula allows astronomers to witness the exact moment a star sheds its layers and transforms into a white dwarf, a process that will happen to our Sun billions of years from now. It also helps us test our models of adiabatic cooling mass loss from stars and the formation of bipolar nebulae, those with the distinctive two-lobed shape seen in the Boomerang Nebula. What makes this nebula even more special is that it is a uniquely observable example of extreme cosmic physics. Most pre-planetary nebulae are too distant or too faint to study in detail, but the Boomerang Nebula's relative proximity and dramatic temperature difference make it a perfect target for telescopes like Hubble, ALMA, and ground-based sub-millimeter telescopes. Every observation reveals new details about its structure, its mass loss history, and the exact mechanisms that keep it colder than the rest of the universe. It has become a benchmark for understanding how cold matter behaves in space, helping us learn about the chemistry of interstellar clouds, the formation of molecules in extreme environments, and the life cycles of stars like our own. As we look to the future of space exploration, the Boomerang Nebula will continue to be a top priority for astronomers. New telescopes and instruments will allow us to map its temperature with even greater precision, track the motion of its expanding gas, and unlock more secrets about the binary star system at its heart. It stands as a powerful reminder that the universe is full of surprises, defying our expectations, and pushing the boundaries of what we think is possible. We once thought the cosmic microwave background was the coldest nature could get, but the Boomerang Nebula proved us wrong, showing us that even in the most fundamental rules of physics, there are exceptions that can teach us more about the cosmos we call home. In a universe filled with black holes, neutron stars, supernovae, and distant galaxies, the coldest place of all is a gentle, beautiful cloud of gas, ejected by a dying star. A quiet, cosmic icebox that challenges everything we know about heat and cold. It is a testament to the wonder of astronomy. Every time we point our telescopes at the sky, we find something that rewrites our understanding, something that makes us feel small, yet connected to the vast, incredible processes that shape the universe. The Boomerang Nebula is not just a record holder. It is a symbol of the endless mysteries waiting for us to discover in the depths of space. Please like, comment, share, and subscribe to the channel